Good afternoon. Today I will be speaking on one photon quantum computer. When we come to the physical realization of quantum computers, we realize that experimental realization of quantum computers has proved extremely challenging. To begin with, we need to know what are the requirements for building a quantum computer. First off, qubits are two-level quantum systems. Not only must we have qubits, but also a supportive system to allow them to evolve as desired. Though, allegorically speaking, a coin is a perfect qubit. Heads up could be a 0 or a 1. But it cannot remain in a superposition state, that is heads and tails, and that is what is unique to qubits. This then brings us to the obvious question, what is actually needed to build a quantum computer? First, we need to represent the quantum information. Number two, we need to perform unitary transformations universally. Number three, we need to prepare a fiducial initial state. And finally, we need to be able to measure the output without killing the cat. A single optical photon is an attractive candidate to be a qubit. Photons are chargeless particles. They do not interact strongly with each other. They can be guided along long distances with low loss. They can be delayed using phase shifters. They can be combined easily using beam splitters. And they exhibit signature quantum phenomena such as interference produced in a two-slit experiment. In principle, photons can be made to interact using nonlinear media. The energy in an electromagnetic cavity is quantized. Its units are h cross omega. Each quantum of energy is called a photon. The cavity can contain a superposition of a 0 photon or a 1 photon. So as a qubit, such a state would read C0 get 0 plus C1 get 1. This is also known as the dual rail representation. Now consider two cavities. Let the total energy be h cross omega. Let the two states of the qubit be ket 0, 1. So the photon is in this state, or ket 1, 0, or it is in this state. The physical state of the superposition would then be written as C0 ket 0, 1 plus C1 ket 1, 0, and this is called the dual rail representation. We can generate a single photon in a lab attenuating the output of a laser. At attenuation, a coherent state becomes a weak coherent state, and a weak coherent state can be made to have one photon with high probability. A better synchronicity can be achieved using parametric down conversion. In this scheme, photons of frequency omega 0 are sent into a nonlinear optic medium, say KH2 PO4, to generate a pair of photons such that omega 1 plus omega 2 is equal to omega. As you can see from this slide and the diagram therein, the parametric down conversion scheme is represented. There is a laser that is incident on a crystal, and the laser beam has a frequency omega 0, and the crystal converts it into two photons of frequency omega 1 and omega 2. Now, the concept is very simple. Whenever we detect a photon of frequency omega 2, we know that a single photon of omega 1 is existing. Of course, this scheme exists in principle, so by coupling the output of the scheme to a gate, which is open when a single photon is detected, and by appropriately delaying the outputs of multiple down conversion sources, we can, in principle, obtain multiple single photons propagating in time synchronously within the time resolution of the detector and the gate. Single photons can be detected with a high quantum efficiency for a wide range of wavelengths using a variety of technologies. For our purposes, the most important characteristic of a detector is its capacity of determining high probability, whether 0 or 1 photon exists in a particular spatial mode. For the dual rail representation, this translates into a projective measurement in the computational basis. In practice, imperfections reduce the probability of being able to detect a single photon. Efficiency eta, which lies between 0 and 1 of a photodetector, is the probability that a single photon incident on the detector generates a photocarrier pair that contributes to detector current. Another important characteristic of a detector is its bandwidth, that is the time responsivity, the noise, and dark counts, which are photocarriers generated even when no photons are. There are many devices for manipulating photon states, three main ones being mirrors, phase shifters and beam splitters, as you can see in the graphic over here. High reflectivity mirrors reflect photons and change their direction of propagation in space, and mirrors with 0.01% loss, that is 99.99% reflection, are pretty usual. A slab of transparent medium with index of refraction n different from that of free space n0 is the simplest phase shifter. Let us consider ordinary borosilicate glass. It has n approximately equal to 1.5 n0. Propagation in such a medium through a distance L changes the phase of the photon by e to the power ikl, where k is equal to n omega upon c0. c0 is the speed of light in vacuum. Thus, a photon propagating through a phase shifter will experience a phase shift of e to the I n minus n0 L omega by c0, compared to a photon going through the same distance through free space. A simple beam splitter is just a partially silvered piece of glass which reflects a fraction r of the incident light and transmits 1 minus r. A laboratory fabricated beam splitter is just two prisms with a thin metallic layer sandwiched in between. And what will happen is it is showing for the states B and B dagger. What are we going to get the resultant as? It is convenient to define the angle of the beam splitter as cos theta equal to r. The angle parameterizes the amount of partial reflection. It has nothing to do with the physical orientation of the beam splitter. The two inputs and outputs are related by A out is equal to A in cos theta plus B in sin theta, whereas B out is equal to minus A in sin theta plus B in cos theta, where classically we think of A and B as being electromagnetic fields of the radiation of the two ports. Nonlinear optics provides a final useful component for this setup. A material whose index of refraction n is proportional to the total intensity I of light going through it. So Ni becomes equal to n plus n2I. This is known as the optical Kerr effect. It occurs very weakly in raw materials as mundane as glass and sugar solution. In doped glass, N2 ranges from 10 to the power minus 14 to 10 to the power minus 7 centimeters square per watts. In semiconductors, from 10 to the power minus 10 to 10 to the power 2. Experimentally, the relevant behavior is that medium. Each beam will experience an extra phase shift compared to what happens in a single beam case. It would be ideal if the length L could be arbitrarily long, but unfortunately it fails because most Kerr media are also highly absorptive, or they scatter light out of the desired spatial mode. It is the primary reason why a single photon quantum computer is unfeasible. And this brings us to the drawbacks of the unfeasibility of a single photon quantum computer. Though the single photon qubit is attractive, it suffers from some serious drawbacks. Photons are simple to generate and measure. In the dual rail representation, arbitrary single qubit operations are possible. However, interacting the photons is difficult. The best nonlinear Kerr media are quite weak. They cannot provide a cross-phase modulation of pi essential for the representation of the controlled NOT gate between single photon states. In fact, because a nonlinear index of refraction is usually obtained by using a medium near an optical resonance, there's always some absorption associated with nonlinearity. With best estimates, approximately 50 photons must be absorbed for each photon experiencing a cross-phase modulation. Well, all is not lost. The upside is that optical quantum computing provides a valuable insight into the architecture of a possible quantum computer. Optical quantum computers appear to be completely interferometer based. The information is encoded both in the photon number and photon phase. Interferometers are used to convert between the two. It is, however, quite possible that the natural home of an optical computer is quantum cryptography and not quantum computation. Even if a single photon quantum computer appeared to be non-realizable, their theoretical formalism is absolutely fundamental in all other realizations such as optical cavity quantum electrodynamics. That brings us to the end of the discussion on optical photon quantum computers. Thank you so much for your time and attention.